In this video, we're going to introduce the Gram-Schmidt process. So I'm going to begin by talking about the idea and what our goal is. So what we want to do is we want to find an algorithm that's going to let us produce or generate an orthogonal basis from any given basis. So it turns out that the best and most efficient algorithm for doing this, for generating an orthogonal basis, is called the Gram-Schmidt process. All right, so let's just dive right into what the algorithm says. So if we're given a basis, x1 up to xp, for some non-zero subspace of Rn. So our subspace can't just be the zero vector. All right, so here's what we do if we want to generate an orthogonal basis. So the algorithm is going to tell us how we produce our orthogonal vectors one by one. So it turns out what we do is, for the first vector, the first orthogonal vector, v1, we just let that be the first vector in our set. We let it be x1. Right, so maybe even let me highlight this. So v1, this is my first orthogonal vector. And we're going to let that just be the first vector in our basis, x1. So v2, the next vector, the next orthogonal vector, it's going to be the second vector in the set, x2, minus the projection of x2 onto the span of v1. And the reason for that is we've seen this type of vector before, taking a vector minus its projection. And we've seen that that ends up being orthogonal to the thing that we're projecting onto. In this case, we're projecting onto v1. So this is going to end up being orthogonal to v1, or I can say to the span of v1. So after I detail the algorithm, the Gram-Schmidt process, I'll draw a picture to explain, well, what's going on here exactly. Okay, but we know a formula for this projection vector. So we have x2 at the front, and the formula for this projection vector is, well, it's x2 dotted with v1 over v1 dotted with itself. So we have that fraction multiplied by the vector v1. Right, so that was the formula for projecting onto one vector. So, okay, so that is v2 right there. So that is v2. v3, let me just go ahead and highlight it right away so I don't forget. So v3 is going to be the third vector in my set, x3. So this is the original set. So the x's are the original basis vector. The v's are the orthogonal basis vectors. So v3 is going to be x3 minus the projection of x3 onto the span of the first two vectors, the first two orthogonal vectors, v1 and v2. And that's really important, because when I project a vector onto a span of a bunch of vectors, those vectors need to be orthogonal. Okay, so, and we know how to do this as well. So we have the x3 in the front. But now, because we're projecting onto the span of two vectors, we're going to have to subtract the projection of x3 onto v1 and onto v2. So x3 dotted with v1 over v1 dotted with v1, and that's going to multiply v1. And then minus, and now we're going to have the projection of x3 onto v2. That's x3 dotted with v2 over v2 dotted with v2. That fraction is going to multiply the vector v2. And so x3 minus this projection vector, this will end up giving us something that is orthogonal to both v1 and v2. All right, so let me also start to highlight these formulas that we have here. So v1 is just x1. v2 is this thing over here. This is v2. v3 is this thing over here. This is v3. Okay, so I actually didn't like the way that blue highlighter was looking there. It was kind of making it a little bit harder to read. So let's keep it highlighted in yellow. So if we keep going like this, we would keep repeating this process until we get to the last vector, the pth vector. So vp will end up being xp minus the projection of xp onto the span of the first sorry, this shouldn't say I should say p. Let's fix that. V sub p minus 1. The first p minus 1 orthogonal vectors. Okay, so if we write out what this is, so we have xp in the front. And now minus the projection of xp onto v1 and then v2 all up to p minus 1. So first let's project x onto v1. We'll get x times, dotted with v1 over v1 dotted with v1 times v1. And then minus dot 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 minus until we get to the last vector. So x dotted with vp minus 1 over vp minus 1 dotted with vp minus 1. And that fraction is going to multiply. So let's just scooch that over a little bit to give us some room. Times vp minus 1. All right. So the key conclusions of this are, it'll turn out these vectors. Let's highlight this last one as well. Let's highlight what vp ends up being. So it'll turn out that v1 up to vp will now be an orthogonal basis for w. And the other key thing about this is that at any step of this process, the span of the first k v vectors is always going to be the span of the first k x vectors. All right, so let's draw a picture to illustrate what's going on here. So I'm going to draw two pictures. So I'll draw a picture of what's going on when we talk about our first two vectors, and then I'll introduce a third vector into it. So let's say if we have two vectors, and I want them to form a basis. So I need them to be linearly independent. So that vector is x1, and let's make this vector x2. And in general, x1 and x2 are not going to be orthogonal. So what the Gram-Schmidt algorithm says is, well, let's start to produce an orthogonal set. So I'll let v1, my first orthogonal vector, be the same thing as x1. It's the exact same. Then what we'll do is, well, let's project x2 onto x1 orthogonally. So this is the projection vector. So that is the projection onto the span of v1. And we're projecting x2 onto the span of v1. So what we need now is we need a vector that is orthogonal to v1. Well, a vector that's orthogonal to v1 is this vertical vector. That one's orthogonal. Okay, but in my picture, let's draw that emanating from here, because all our vectors have to emanate from where the origin is. Okay, this vertical vector, that is definitely orthogonal to v1, so this is going to be the vector v2. But notice that that's the same thing as just this red vector, but after I've just translated it, after I've shifted it. So v2, in other words, this red vector here, also is just x2 minus that projection vector. And let me just write proj, and then period, so I don't have to write out this whole thing. So that's what v2 is. It's x2 minus the projection. And that's what we were seeing in that Gram-Schmidt process. That when we define the next vector in our set, the next orthogonal vector, we take the previous vector, in this case x2, minus the projection. So, well, what does it look like when I add three vectors into the mix? So I'm going to make this three-dimensional, my picture. Imagine that we have this plane, and let's say that x1 and x2 both lie in this plane. And let's just actually say that we've already made the first two vectors orthogonal. So we've already found v1 and v2. So maybe v1 looks like this. So let's say that v1 is already like that. And then v2, let's say we've already found v2 and made it orthogonal. So let's say that this is a right angle right here. Let's say that that is the vector v2. That is v2 right there. All right, so now let's draw an arbitrary third vector, x3. So in general, this is not going to be orthogonal to those other two vectors. So this right here is x3. Well, now let's project this down. If we project this down onto that plane, here is the projection vector. So this is a right angle. So this is the projection vector. So this is the projection. This time we're projecting onto the span of v1 and v2. And what is it that we're projecting? We're projecting the vector x3 onto that span. All right. So what we want now is we want an orthogonal vector, a vector that's orthogonal to both v1 and v2. So that is this vertical line right here. This vertical line is definitely orthogonal to v1 and v2. So if I draw that now emanating from where the origin is, so here's the origin. So I draw the exact same vector in the same direction, just going up. This red vector, that is what v3 is going to be. So v3 is this red vector. And this is x3 minus the projection. Minus the projection, in this case, we're projecting onto the span of v1 and v2. But notice that that has the same format that we saw in Gram-Schmidt. Basically, each time we want to form the next vector in our orthogonal set, you take xp, whatever that is, minus the projection of xp onto the span of the previous orthogonal vectors. All right, so let's do an example. All right, so let's let x1, x2, and x3 be these three vectors. It turns out that, just fix that because my set had written v's when I meant to write x's, because these vectors are x's. So it turns out that x1, x2, and x3, this forms a basis for R3. So in part A, let's construct an orthogonal basis. So let's use the Gram-Schmidt process. So it says, let v1 be the first vector in this basis. It's just going to be x1. And x1 is 1, 3, 0. So it starts off pretty simple. Now we're ready for v2. So v2 is going to be x2 minus the projection onto the span of the previous orthogonal vector. So the span of v1. And what is it that we're projecting? We're going to be projecting the second vector in our basis, x2. So let's write out what this is. So this is x2 minus, and then the projection formula will be x2 dotted with v1 over v1 dot v1. So that fraction times the vector v1. So it's super important here that I'm using v1, not x1. So over the course of doing Gram-Schmidt, when I subtract away these projections, I got to make sure that I'm projecting onto the span of the v's. Because when I form a projection vector, the span here, I need to be projecting onto a set of orthogonal vectors, a span of orthogonal vectors. And the v's are going to be orthogonal, but the x's are not. So it's really important that I put v1 here and not x1. It turns out that at this step, it doesn't make a difference because v1 and x1 are the same. But at the next step, when I get to v3, it will make a difference. So it's better to keep this good notation from the beginning. All right, so now let's start to evaluate this. So what is x2? x2 is the vector 0, negative 2, 4. That was up here. If I dot x2 with the v1, so I'll get 0 times 1, which is 0. Negative 2 times 3, which is minus 6. 4 times 0, which is 0. And then over the denominator, which is v1 dotted with itself, so 1 times 1 is 1, 3 times 3 is positive 9, 0 times 0 is 0. That's v1 dotted with itself. Times v1, which is 1, 3, 0. Alright, so let's simplify. So simplifying this, so this fraction right here, so we get negative 6 on the top, 10 on the bottom, and then with the negative in front, this will actually simplify to positive 3/5. So we're going to get some fractions here. So here is an important tip. When you do the Gram-Schmidt process, when you encounter fractions, you can simplify your work if you factor out the fractions. So this will be useful. Let's go ahead and factor out what's making this a fraction. So I'm actually just going to factor out the denominator of this fraction, the 1/5. And if we do that, what I'll be left with in this first vector spot is I would have to put a 5 in front of that. So 5 times the vector 0, negative 2, 4. 0, negative 2, 4. I got to put a 5 there because I factored out a 1/5. Okay, and then in the next spot, I factored out this denominator, so we'd still be left with the plus 3 that we had. Plus 3 times the vector 1, 3, 0. All right, and now let's simplify this. So we have 1/5. So we have 1/5 times this vector. So if we add these vectors together, I'll get 0 plus 3 first, which is 3. Negative 10 plus 9, which is negative 1. And then 20 plus 0, which is 20. All right, so we end up with this vector, and this has fractions. So at this point, we have two options. We could continue with the two vectors that we've produced at this point. So the first vector, remind ourselves, that was 1, 3, 0. And the second one now is 3, negative 1, 20. So we could use these two. Or what we are allowed to do is we're allowed to scale the vectors that we have if we want to get rid of fractions. Or, so I don't need to do that with the first vector. Oops, and I forgot to write the 1/5 in front. So let me give myself a little bit of room here, and let's write in that 1/5, because I forgot to do it before. Okay, so the other thing that we could do is we could keep the first vector the same, 1, 3, 0. But I can scale the second vector by 5. And if I do that, I'll have 3, negative 1, 20. So let me make a note of that as well. So we can scale vectors by multiplying by a scalar. We can scale vectors to simplify when necessary. When necessary. Okay, so in this case, I multiplied the second vector, multiplied it by 5 to get rid of the fraction. So I have the choice. I have the choice of using the set with the 1/5 in front or using the set without the 1/5 in front. So I'm going to go ahead and use the version without the 1/5 in front because that has all integers and that looks simpler. All right, so at this point, v1 is this vector right here. This is v1. And I'm going to say that v2 is now this vector. So it's not the version with the 1/5 anymore. I've decided to scale it, and v2 is going to be this. All right, so let's keep going with our Gram-Schmidt. All right, so we are ready for v3. So v3, let's give ourselves a little bit more room. So I've already gone ahead and written down the formula for v3. It's going to be x3, the third vector in my original basis, minus the projection of x3 onto the span of v1 and v2. So notice it's v1 and v2 and not x1 and x2, because I need to project onto a span of orthogonal vectors. So let's write down the formula for this. So I have x3, and then minus, first we'll project onto v1. So we'll get x3 dotted with v1 over v1 dotted with v1. That fraction times the vector v1 minus, next we project x3 onto v2. So we'll get x3 dotted with v2 over v2 dotted with the v2. So that fraction times the vector v2. All right. So I've gone ahead and worked out some of these dot products because that's just arithmetic at this point. We could check this. So we end up getting the following. So for example, x3 was the vector 4, 2, 0. Sorry, 4, 2, 10. You know what? I don't think that's right. 4, 2, 10. That might have been a carryover from what I'd written before in the race. Forgot to erase. Yeah, x3 was 7, 0, 1. Let's go ahead and fix that. So 7, 0, 1. So this should be 7, 0, 1. 7, 0, 1. But I think the rest of these dot products and these other vectors that I've written in are the same. Okay. So now if we simplify this, we get the following. We get 7, 0, 1. This fraction has become this negative 7 over 10. This fraction over here ends up being negative 41 on top. 410 on the bottom. I guess technically I should say it's 41 on the top and the negatives in front of the fraction. But then that simplifies to negative 1 over 10. That's how we got the negative 1 over 10 here. All right, so we are almost done. Let's just simplify this a bit more. So just like we did before when we had a fraction, let's go ahead and factor the fraction out. So the thing that's making this fraction is this denominator, the 10. So let's factor out a 1 over 10. So 1 over 10 factored out. So when I factor that out of this first vector, I have to put a 10 in front of it. So 10 times 7, 0, 1. For the next term, we'd have minus 7 times the vector 1, 3, 0. And for the last vector, we just have minus 3, negative 1, 20. All right, so we're almost there. Let's simplify this. So we have 1 over 10 times what? If I multiply the 10 in, first I'd get 70. From the next entry, I'd have minus 7. From the next vector, I'd have minus 3. For the second entries, I'd get 0. 7 times 3, 21, so minus 21. And then double negative gives me plus 1. Third entries, 10 times 1 is 10. 7 times 0 is 0, so minus 0. And then I have minus 20. All right. So what we have is we have 1 over 10 in front. And then I get 60 for the first entry, negative 20 for the next one, and then negative 10 for the last one. And this is really nice because all of these are divisible by 10. So if I distribute the 1 over 10 in, we get 6, negative 2, negative 1. And that is our third vector right there. This is V3. Let's write that a bit better. So this is V3. And at this point, we have our orthogonal set. So here is our orthogonal set. So these are the 3 orthogonal vectors that we have produced using the Gram-Schmidt process. All right, so I just moved that over to give myself a little bit more room. So let's end this video by now constructing an orthonormal basis. Now that I have this orthogonal set, let's construct an orthonormal basis. So once it's already orthogonal, normalizing it is actually really easy. We just need to divide each vector by its length. Or another word for length is magnitude. So let's find the length of each vector. So the length of V1 will be 1 squared plus 3 squared plus 0 squared square rooted, and that is root 10. The length of V2 is going to be 3 squared plus negative 1 squared plus 20 squared square rooted. So this is 9 plus 1, which is 10, plus 410 square rooted. And then finally, the third vector, V3, its length, that's going to be 6 squared plus negative 2 squared plus negative 1 squared square rooted. So this is 36 plus 4, which is 40, plus 1, which is 41. All right, so we get square root of 41 here. So our orthonormal basis, we are ready to write down what that would be. Let me zoom out a little bit so I can see my original vectors. Our orthonormal basis is going to be, so we multiply the first vector by 1 over root 10. 1 over root 10 times 1, 3, 0. The next vector we multiply by 1 over root 410. That multiplies 3, negative 1, 20. And the last vector we multiply by 1 over root 41. That multiplies the 6, negative 2, negative 1. And this is an orthonormal basis. In general, if we're given a basis and we want to form an orthonormal basis, make an orthogonal basis first, like we did using Gram-Schmidt, and only after you get it to be orthogonal, then go ahead and normalize each one. It'll be much simpler computationally if you wait until it's fully orthogonal before normalizing it.